Hi everyone, in this video I will be discussing my Choose Your Own Adventure lab. For this lab, I chose to investigate a man jumping on a trampoline who may or may not defy the laws of physics. So the objectives for this lab are to track and record the motion of a man on a trampoline, simulate his motion through computer code, compare the real world and computer simulated motion, and discuss his motion in terms of the energy principle. The physics principles we will be using are Newton's second law, so we will be using the velocity update and the position update formulas. We will be using delta KE trans is equal to 1/2 mv final squared minus 1/2 mv initial squared. We will be using delta energy is equal to delta KE trans plus delta UG, which is equal to work. And we will be using the law of conservation of energy, which says that the total energy of an isolated system is constant. This is Christoph Hamel, and he is jumping up and down on a trampoline with incredible height. He hits the trampoline, and while he's in the air, he makes contact with a wall and he flips in the air. This is the data collected from Tracker. We will use our code to simulate the Y motion, since that is the motion that may or may not violate the energy principle. We don't really care what Christoph's side-to-side motion is. So for our initial conditions, we set the mass of the ball equal to 90.719, and we set our initial position and our initial velocity. So for the code, we need to calculate translational kinetic energy, gravitational potential energy, and the total energy. Since our system is Christoph and the trampoline acts somewhat as a spring, so we also need to calculate the spring constant. We need to choose a very stiff constant because the spring only reacts when Christoph's weight hits the trampoline, so the velocity moves in the opposite direction very quickly. We are going to make L0 small because if you lightly press on a trampoline, you will not feel the trampoline move immediately, but after a few seconds. Then we will make a while loop that will run until the end of our recorded time. We set our initial energies equal to the energies themselves. We calculate the gravitational force, which is also the net force. When we look at the tracker video, we see that the lowest y coordinate is about negative 5.4 meters. So we say that if the y position is less than negative 5.4, L is the absolute value of the y position minus 5.4. The spring force is Ks times L minus L0 y hat, and the net force is both the force of gravity and the spring force. We also need to account for when Christoph is slowing down at the top of the wall and flipping. To do this, we say that if his height is above negative 0.4 meters, we slow his velocity down by 60% as a rough estimate. We then use Newton's second law to update his position and velocity. We will then calculate the energy changes by subtracting our initial energies from our final energies. So when we run the code, we can compare our two models. The real-world model and the computer-simulated model could be slightly off due to factors such as me having to estimate Christoph's and the wall's height, the spring constant, and the relaxed length of the spring. So in this graph, we see the change in our energies. We can expect the gravitational potential energy's amplitude to be consistent throughout because gravity is a constant force. The amplitude of translational kinetic energy is based off of where Christoph is in relation to the trampoline. Sometimes he falls further or bounces back up less, which explains the slight difference in amplitude. When he falls, the change in kinetic energy is positive. When he's bouncing back up, the change is negative. The opposite relationship is true with gravitational potential energy. The spikes in the change in overall energy occur whenever Christoph hits the trampoline. The law of conservation of energy states that for isolated systems, energy cannot be created or destroyed, so that would lead us to assume that the orange line should just be a straight line at x equals 0, but that is not the case here. So what does this mean? Has Christoph violated the law of conservation of energy? The answer is no, because the system is not isolated, because it consists of both the jumper and the trampoline. So in this case, the change in energy is equal to the work in our system. In our scenario, work is equal to the change in translational kinetic energy and the change in gravitational potential energy. So what if we model Christoph as a point particle? Well, when we choose a point particle as a system, the change in energy is only equal to the change in translational kinetic energy, so we would not account for the gravitational potential energy. Instead of modeling the trampoline as a spring, we would just model it as a mirror. When the jumper hits his lowest point, we would set ball.vel equal to negative ball.vel. Because this was greatly simplified from our actual code, this prediction would not be nearly as accurate as our final product.